Hey everyone, how are y'all doing? Today we're gonna check out the Leetcode problem. This question is very popular, often asked on Amazon, Facebook, and many other companies' interviews, and it just gives a great deal of understanding about time management problems in general. So let's crack straight into it. So today we're gonna be solving meeting rooms 2. We're given an array of meeting intervals, where each interval is basically a pair of start and end times. We have to return the minimum number of the conference rooms required. First, we have to find an intuition, but before we dive into that main idea, I want to give you a quick tip. Some interviewers don't like to disclose the constraints to their interview problems because in some cases you can infer the magnitude of the problem based on the length of the input or other properties. For example, in this problem, the interval length is between 1 and 10,000, so it's quartic, which is not a terribly big number, but also not very small, which means that you can't just attack this with anything because it might turn out to be too slow. With 10,000 elements, the solution is generally somewhere between the quadratic and the logarithmic range. There is a great article on Codeforces that details how you can often guess the complexity just by looking at the constraints, or most likely asking for them in the interview setting. Of course, this is not guaranteed, but an awesome thing to be aware of. I'm gonna put the link into the description. So how can we build an intuition for this problem, you may ask? I think let's start drawing and see how this works out if we sketch up one of the examples. Let's take a look at the first example in this problem. So there will be 3 intervals in this list. The first one starts at 0, ends at 30, the second one starts at 5 and ends at 10, and the third one starts at 15 and ends at 20. Let's try to sketch these up in this basic timeline. I'm gonna use the red marker for the first interval. It starts at 0 and will end at 30. Let's use green for the second interval, which will start at the 5 and end at 10. And let's use blue for the third interval, which will start at 15 and end at 20. So let's mark these a little bit more just for the sake of clarity. It will be easier to see what is happening here. So what we can see here is that the red interval will take up 1 room for the entirety of these 30 units, and the green and the blue intervals will take up 1 rooms. But since the green room will be released at the 10th unit, the blue room can reuse it. So even though they need 1 room, basically they will only use 1 room, and in combination with the red interval, this means that it will only take 2 rooms in total for the entirety of the 30 units. How can we formalize this logic? At first we know that 1 meeting room is definitely needed because of the red meeting. Then by the 5th unit we need another meeting room. That's 2. If there weren't any other meeting scheduled, we would say that the answer is 2, but we have 1 more. So since the second meeting ends before the third one started, we know that nobody needs the room anymore and it can be reoccupied. In other words, when we put the new meeting into this timeline, we have to ask, will the previous meeting end before the next one starts? If yes, then we don't need an extra room. If not, then we have to keep digging for new rooms. How can we keep track of if the previous meeting has ended before the new one starts? We keep track of the minimum times when the meetings end. For example, for the red meeting, it's going to be the 30th unit. For the green meeting, it's going to be the 10th unit. So if we want to add the blue meeting here, we want to see that it's already past the green meeting. And of course, we need to know it as soon as possible. Keeping minimum value with fast retrieval, the minimum priority queue or heap comes to the rescue. The minimum heap is a tree-based data structure, and its main benefit that it will always keep the lowest value in the root of the tree and all others ordered below that. Inserting a new element into this heap takes logarithmic time, so it will be big O of log n, and reading the top element of the heap is constant time, so it's big O of 1. The algorithm behind the mechanism of the heap structure is probably worth another video in itself, so I'm not gonna go into details right now, but let's try to construct this min heap based on the example. We know that the first meeting ends at the 30th unit, so let's add 30 to the heap. The next question is, Does the second meeting start after the previous one has ended? No, because it is overlapping. So the second meeting starts at 5, but since red is still going on, it is overlapping. Which means that the next meeting we want to keep an eye on is the one that ends at 10. So the second meeting has to be added to the heap. And because the second meeting ends earlier than the first meeting, it is going to be the new root for the heap. The next question, does this third meeting start after the previous one has ended? And yes, because the third meeting starts at 15, the second meeting ends at 10, so they are not overlapping with each other, which means we can discard the previous meeting that has ended at 10, but we are still going to keep an eye on the minimum, which is going to be 20. This means we have 2 rooms again, and there are no other meetings. Okay, but what is the time complexity for this? The worst case scenario is that all of the intervals will overlap with each other, and we have to make n inserts into this minimum heap, where n will be the number of the intervals, and also in the worst case, we may have to discard the minimum value n times. So the time complexity overall is going to be big O of n times log n, where this n is going to be the number of the intervals, and the log n is going to be the time complexity for inserting a new element into the minimum heap. And the space complexity is going to be big O of n, where n is going to be the number of intervals. We may have to add the intervals into the minimum heap n times. This example is very simple because all of the intervals are given in a sorted order. In the first example, you can see that the first interval starts at 0, the second interval starts at 5, the third interval starts at 15. So it's kind of easy to put them into this timeline, but if they weren't and there would be hundreds or thousands of intervals, it wouldn't be so simple and we wouldn't be able to see the overlaps that easy. So the first thing that we should do here is to sort the intervals by the start times. Okay, I think this pretty much sums up the intuition for this problem. We can jump into the code right now and see how that works out. This is the class that we get from Leetcode when we open up this problem. There will be one method here with the input parameter of an integer matrix, which is basically a 2x(n) matrix for the start and end times. And the return type will be an integer that will tell us the minimum number of meeting rooms required. At the end of the intuition building phase, I already mentioned that we should sort the intervals by their start time because it will be easier to see the overlaps. So I'm gonna start with that. I'm gonna sort the intervals, and based on this lambda expression here, I'm gonna take the first property, which is the start time. It is indexed by 0, and sort based on that. After that, we can start building the priority queue, which is the minimum heap in Java. It is going to store integers. I'm going to call it mpq as minimum priority queue. And after that, we can start by adding the end time for the very first interval. So this is guaranteed to be there in the intervals because based on the constraints, one interval is guaranteed in this matrix. And after that, we can start by iterating through the remaining intervals, starting from the first based on the index. And we have to check whether this new interval's start time is after the minimum end time that we store in the priority queue. We have to also make sure that the priority queue is not empty. We don't want to get any accidental null pointer exceptions. the ith interval's start time is bigger or equal than the minimum priority queue's top element, which is going to be the peak. If it is, then we know that we can discard the element in the top of this minimum heap. So let's get rid of this. And after that, we can replace it with the end time of this ith interval. So we already constructed this minimum priority queue, and at the very end of this algorithm, we know how many meeting rooms we needed because it will be stored in the minimum priority queue. And the size will tell us how many meeting rooms are necessary. Let's submit this to make sure it works and see how it performs on Leetcode. So although it isn't the best performing solution, it is definitely a great algorithm to know. But once again, what will be the time and space complexity of this solution? So sorting is going to take big O of n times log n time, because there are n elements in these intervals. Constructing this priority queue, adding a new element is going to be big O of log n. Worst case scenario, we will have to add all of them, so it will be n times log n. Peaking the top element of the priority queue is going to be a constant time operation, and removing the minimum element from this is going to be log n again, but worst case scenario, we have to remove all of them, so it's going to be n times log n. So in total, the whole algorithm is going to be big O of n times log n. But what about the space complexity? As I've already mentioned, the worst case scenario is that we have to add all of the intervals to this priority queue, which is going to be big O of n, where n is the length of the intervals. I hope this was helpful. If it was, please like and subscribe, leave a suggestion or a comment. This was my very first video and I'm aware of all the editing mistakes made, and I really hope I will have more time to spare for this little project because I really enjoy helping the community and solving problems, but this format is definitely different than writing. Bye!